All right. Hello, everyone. Welcome back to Comp 3430 Operating Systems. I hope that you are all doing great today. I have recently noticed that at 5 p.m. it is no longer dark outside. Things are getting better. It's improving, and I'm really, really happy about that. I took my kids last night to an elementary and middle school presentation of the musical Madagascar. I'm not sure if you've seen this movie before. Have you seen Madagascar before? Many of you have seen Madagascar. It's about these animals that live in the New York Zoo that escape. Some of them more on purpose than others, but the idea is that they make their way in a shipwreck to Madagascar, and then eventually they do get back to the zoo in New York. But one of the funniest parts of this movie to me is the inclusion of these penguins that are just like these army, really gruff sounding army folks, and giving direction and orders to the other penguins. And yeah, that joke doesn't land very well when it's a 12-year-old kid doing the voice of the penguin. But it was good, and everybody had fun. It was a good show. The kids were working hard, and my kids actually liked it, and that's telling of the quality of the show. So yeah, welcome to my personal life. This is what I do in my spare time. So in class on Monday, our goal was really to, here are some RAID levels. Here are some workloads. Let's try and make decisions about what RAID level is going to be best for that specific workload. Today, I want to summarize that, because a lot of it was me I'm going to tell you what the workload is, and then take your response, and then verbally explain to you what that is. So I want to formally summarize what my thoughts on this are. But the goal for you is I should be able to give you a workload description on a test, for example, and you should be able to tell me why I should pick this RAID level, and then also why I shouldn't pick these other RAID levels. So convince me as this person to choose this specific RAID level for this specific problem. The other thing that I want to move on to today is I want you to be able to describe what a human operator might see in files when a file system is in an inconsistent state. So RAID as a whole is at a pretty low level in terms of the way that our operating system interacts with it. In fact, we can go as far as to say that our operating system actually has no idea that there is a RAID underneath it. That RAID controller that I brought to show you last class, the OS sees this as a drive. That's all it knows about this. It doesn't know anything about the RAID underneath. What our operating system does know about is file systems, and our RAID actually has no concept of file systems. It doesn't know anything about what you're asking it to write. It doesn't care. All it knows is if you ask it to write this thing, it needs to duplicate it across all these drives, or pick which drive it's supposed to go to, or some combination of the above, or calculating parity bits, or whatever. It doesn't know the difference between write the super block and write this picture of a cat. It doesn't know the difference between these two things. And so in terms of maintaining consistency with file systems, RAID is not a good solution. It's not going to help us with that. It's going to help us save our data or have bigger size capacity disks, but it's not actually going to let us do anything with file systems because RAID doesn't know anything about file systems. So I want to spend some time taking a look at the two file systems that we've looked at so far in this course. So the conglomeration of VSFS and ext2 and exFAT. Start to think about the data structures that are being changed when we're making changes to a file, so when we're appending to something. And then I want us to think about what happens if we change only some of those data structures before our machine crashes. So we're only partially updating the data structures, and what that would actually look like to a person that's using the machine. This is all very related to this learning outcome that we had in the 2 weeks about file systems of show how common file operations are performed in terms of manipulating a file system's data structures. Although what we had been focusing on there was what do we refer to when we're reading a file. Today, we're going to be spending a lot more time thinking about what are we actually making changes to when we're changing the contents of a file. So when we're doing write operations to a file system. All right, so this is going to be, like I said, a verbal summary of what we did last class to give you some formal statement of what I think about each of these different situations. So the first scenario that we looked at was this data hoarder. And this is basically, I can only afford really small disks, but I need to have lots of capacity, and maybe I want to have a little bit of reliability, but that's not really my primary concern. So the summary of this workload is, I can't buy these large drives. I'm either too cheap or too poor, and I just can't afford to buy them. The data is important, in air quotes here, it's important data, but this is replaceable data. This is something that I could get back afterwards if I wanted to. When I'm thinking about data, there's replaceable data and there's irreplaceable data. Replaceable data is like programs and stuff. I can reinstall my programs. Replaceable data is stuff that I've backed up off the internet. It's something I can get back again if I want to later. Irreplaceable data is like schoolwork. I mean, it's painfully and tediously replaceable. You should be able to recreate your program that you've written for this assignment, but it's painful. I cannot replace pictures of my children. If I lose a picture of my kid, that's completely irreplaceable in terms of I only have it stored on disks. It's completely irreplaceable. So this data is important, air quotes, but it's replaceable. And so the best options that I have in my head, and I think that we agreed on this, is RAID 0, just maximize capacity and don't actually care about any reliability whatsoever. Take all the disks that you can fit and just make them one giant drive so that you have as much capacity as possible for this person. Maybe sacrifice some capacity for a little bit of reliability. So second choice here is RAID 4 or 5. Sacrifice one of your disks for parity, but don't sacrifice all of your disks to duplicate all of your data, because this is replaceable data. This is something that I can get back later if I need to get it back later. We're okay with this one? Okay. The next one was the gamer, and the gamer was basically speed at any cost. The drives that this person has are just, they're not fast enough. And I was politely corrected after class that drive speed has nothing to do with frame rates. Fair enough. Drive speed maybe does have to do with like moving between different parts of this large open world application. So I'll change this scenario just a little bit. You know, there's some reason why I need to have fast drives in this thing and not a fast GPU. But these drives are just not fast enough. The data is fully replaceable. So this is a program, and all of my save data is stored in the cloud. Like, there's nothing for me to worry about in terms of replaceability here. Everything is fully replaceable. So I don't care at all about reliability of the data that I'm putting onto this array. So the primary goal that this person has is really just to maximize performance, make things as fast as possible. And the way that we can do this is I'm going to say RAID 0 or RAID 1. And I'm going to say that this is theoretically to improve the read speed without having to worry about write performance at all. So theoretically, if we're choosing RAID 0 for this person, so striping, we're going to take data and we're going to spread it across disks. And theoretically, for a random workload, I'm just like rapidly moving between different places on the file in this open world game. Loading the assets might be spread across many different drives. The RAID controller could theoretically be able to respond to many different requests for random data in parallel. In practice, it's going to be as fast as the fastest drive. Same thing with mirroring with RAID 1. In theory, our RAID controller could accept many read requests and then respond to them all simultaneously, just asking each different drive to give it back some different data. If it's smart enough to do something like that, theoretically, it could have its own memory. It could be predicting things like this. It could be making these parallel requests. Theoretically, then, for sequential read loads, then we would get maximum performance from all the drives all at the same time. In practice, our disk is probably just going to be the fastest disk in the system. We don't really want to do RAID 4 or 5 with this one. We don't want to have to worry about calculating or testing whether or not the parity is actually the correct value. We don't want to do that when we're reading it. So we're not going to do something like that. That make sense for everybody? Okay. Here's the last one. This one was the scientist. This was the scientist that was working at the science factory, working on important science. And the summary of the workload here was intentionally like, there's different constraints that this person is trying to pull on. I'm very intentionally trying to do this here. The first summary of their workload is that they do need some very large capacity fast storage. They need this for their temporary results. So the things that are being calculated like while the calculations are happening. So this is not something that's super important for them to keep in the long term, but they need lots and lots of disk space, and they need it to be very fast. This is at odds with the other part of their workload, which is I need reliable long-term storage. I need to have both of these for the thing that I'm doing. But if we're to draw like the traditional triangle of capacity, reliability, and speed, you pull on one and you can't like pull on all of them to stretch this triangle out. The other ones are going to have to kind of push in to fit where that other thing is. So this person has two very different need sets. They need to have large capacity temporary storage, and they need to have reliable long-term storage. They've got multiple different goals, maximizing capacity and then separately maximizing reliability, but these are for two separate parts of their workflow and their workloads. The best options to me were to have one RAID array that's RAID 0 for temporary results. Make a really big disk that can store these temporary results fairly quickly for this person, and then when the calculations are done, move it to a different RAID array, one that's RAID 1, that gives them maximum reliability so that when someone is questioning them about their results in their paper that they published in the important journal, they're able to reproduce the data that they got from the workloads or from the experiments that they happen to be doing. An alternative here is use advanced file systems. So don't even think about using RAID. Use something like ZFS to work on your drives, and then use software RAID effectively to do it. But I'm going to say that in terms of the answers that I am thinking about here, this outcome that I'm assessing you on is specifically tell me what RAID levels are appropriate. Picking ZFS is kind of like not really actually satisfying that learning outcome. I really care about RAID levels here as opposed to advanced file systems. All right, okay, any questions about these? All right, okay, awesome. I'm going to go back up to the data hoarder here, and I'm going to say that I have to insist that you read this book series called The Expanse. I have to insist that you do it. Has anyone actually read it already? Okay, homework for the final exam. You must read The Expanse now. Okay. All right, so what I want to do now is I want to talk about file systems again. Like I said, RAID and the idea of inconsistent file systems are kind of like operating at different levels. RAID is this purely hardware approach to solving a problem, but RAID has no concept of file systems. It's unable to distinguish the difference between important file system metadata and unimportant cat picture data. There is no difference to it. It receives write requests with a blob of data and nothing else. File systems kind of know about themselves. They must know about themselves to be able to recover data from a drive by making read and write requests. And so the read and write requests that our operating system is making are going to be like a series of read and write requests to make changes to data structures and to make changes to the data that we're actually putting on this disk. File systems can become inconsistent in creative ways, and inconsistency here is specifically related to the file system's metadata and the file system's data structures itself. File system consistency never has anything to do with actual data. Our file system, in terms of consistency, does not actually care if I've corrupted your data. That is not an important part of file system consistency. The only thing that's important about file system consistency is that the data structures all agree with each other about the data that's on the drive. What I want to do is really briefly look at our two file systems again and think about the kinds of data structures that would need to be updated when we are extending an existing file. So there is a file on the file system already, and I'd like you to use your mind theater to imagine this. I open up Microsoft Paint, I open up a picture of my cat Walter, and I make the canvas just a little bit bigger, and now it's big enough to move on to another block or to move on to another cluster. The file already exists. I've opened it, so there are existing structures in my file system that represent this file and its file name. I'm adding more data to this file that's already there. So let's pop over here. And what I want to do is take a look at this, the structures that we've got here in terms of I want to make a change to an existing file. So our current operation here is append to an existing file. First, we're going to open this thing, and then we're going to write to that file. So open to get a file descriptor, and then write to actually add data to the end of this file. In terms of VSFS and ext2, after we've opened the file and we're starting to do the write operation, the data structures that become important to us are going to be the data bitmap itself, the allocation structure. We're going to be referring to this to find an unused block. We have to use this to find an unused block, and the allocation structure that we have here right now says that blocks 0 through 5 are currently used. So these bits are set in this allocation bitmap. Blocks 6 through 9 are unused. These are unset bits. These are zeros in our file system. When we make a write operation to this, we're going to need to make a change to the inode table itself. Specifically, we're going to need to make a change to the inode for this file. We have to change this file's inode in two ways. One is to change the file size of this inode, or of the data that this thing points at. So there'll be a property in here that says this is how many bytes this file has in it. I also am going to need to make a change to my direct block pointers here. I'm going to extend this file. I'm going to add a new block, so I need to add a new block to my list of direct block pointers. Then I'm going to need to make a change to the actual data region. So the data region part that I'm going to be writing to here is, let's say that I'm making a picture of me beside Walter because we're best friends, and you know, despite him biting me all the time, I love my cat. I don't like that he bites me, but I do love my cat, yes. Making a change to the data region, to the data bitmap here, our allocation structure, this is effectively going to be one write operation to my disk. It's a block, but we're going to be able to make that change with one write operation. We're going to be able to write one sector to our disk, and we're going to have that change appear. I then separately have to make a write to my disk for the inode table. I'll make changes to it, I'll read it, and then I'll write my inode table back out with the changes that I've made to the inode structure itself. And then I'm going to separately make changes to the actual data region. I'm going to write the bytes that I created by drawing myself in Paint to the actual data block number 6 to make changes to the file. We could technically and theoretically also be making changes to block number 5 here, but I'm going to pretend that we don't have to care anything about like the bitmap file format right now in terms of updating its own internal structures, because that's outside the scope of what we're thinking about. We do not need to make changes to the root directory's directory entries. We don't need to make changes to that structure in this file system because the only thing that this really has is the name of the file and the file name's length. If I were renaming the file in this directory, I'd need to make changes to that, but I'm just saving to this existing file. So I don't need to make changes to any of the directory entries in this file system right now. Okay, so this is VSFS and ext2. The other file system that we've been looking at here is exfat. And I'm going to say that the operation is the same thing. We are extending an existing file here. We've got the main boot record, which contains the main boot sector, that small 512-byte structure that represents metadata for this whole file system, and then the file allocation table, the FAT. We are actually technically going to need to make changes to the main boot sector, possibly because the main boot sector tells us how many bytes are free on the file system, but we're going to ignore that for now. We're going to pretend that that's not happening. This might also be happening for VSFS and ext2, but we're just going to pretend that that doesn't happen. We are going to need to make changes to the FAT. This is one of the things that we're going to have to make changes to because we're going to have to add a new cluster to the cluster chain for this file. There is an existing cluster chain, but it's one entry and it's FFFFFFFF. It just says that there's only one cluster currently in this thing. I'm adding a new cluster to the end of this file, putting a picture of myself in here. And so I need to add a new cluster to the cluster chain for this file. exfat also has an allocation structure. It has an allocation bitmap. The allocation structure for exfat is a directory entry in the root directory. If you've started looking at these directory entries in the root directory, you will have found the directory entry that is allocation bitmap. The allocation bitmap is the same as the allocation structure in VSFS. It's that data bitmap. This is effectively what this is. But the allocation bitmap directory entry says the first cluster of this data structure is in cluster 3. So cluster 3 in my file system then here is going to actually be the allocation structure. So the allocation structure is in the cluster heap for this file system. And right now it says clusters 2, 3, and 4 are used. They are set to 1. These are currently occupied by other things, the root directory and the allocation structure itself, so they cannot be used. And then cluster 4 is used for the first part of this image that I've got. So we're going to need to make changes to this to say that we are going to use cluster 5. Then I'm going to need to make changes to the stream extension for this thing, because the stream extension tells me how many bytes are in this file. And then I'm going to actually have to write the data out. I'm going to have to add the data for the cluster for this new picture of me amended to this picture of my cat Walter. So writing the FAT, then writing the allocation bitmap, then writing the stream extension, then writing the data section for this, actually writing out the cluster here. These are going to be at least 4 separate operations that we're going to need to make to represent our file in this file system, represent the changes to our file in this file system. We're not changing the name, so we don't have to change the other things about this. We don't have to change the file name entry in this directory entry structure or entry set, but we do have to change that stream extension to indicate that there are more bytes in this file right now. Are we all okay with these changes? Okay. So now what I want to do is I'm going to switch over to my slides here. A crash can happen in between any of these write operations that we're doing. So a crash can happen after I've written the inode, and then I haven't done anything else with the data bitmap, and I haven't written the data itself. A crash could happen after I've updated the FAT and nothing else. A crash could happen after I've made changes to the stream extension and nothing else. That might be the only change. It could be that I've updated the stream extension and the data, but not updated the FAT or the allocation structure for this file system. There are 4 different results that can visually happen to these files in our file system. The file looks corrupted, so I've been able to do some of the stuff, but I haven't been able to make changes to the content. It's just whatever happened to be there before I made these changes. The file size is bigger, So the report that we see in our Visual File Explorer says there are more bytes than there were before in this file. There's less space available on the volume. So our allocation structure is telling us that there are more blocks or clusters used than there were before, or there's no apparent difference. Something has changed, but we can't see anything right now about what this thing is going on. One or more of these different results can happen. I'm going to go through some situations here with these are the structures that were updated, and I'm going to ask you to answer which of these options are going to be the results that we see in our File Explorer. All of the options are going to look like this. This is a corrupted looking file. This is me having added myself to the picture, but then Walter is gone, or some vice versa option of this. This one is going to be, there is fewer available blocks on the file system, so there's less space on the file system itself. So this is representing like a C drive, and it says there's this many bytes free, and now it says there's this many fewer bytes free than there were before. It could be that the picture itself has got a bigger file size, and I'm just saying block here to say, there's more bytes than there were before, but I'm not specifying 300 bytes versus 700 bytes. This is just, it's bigger, the picture is bigger than it was before, or there's no apparent difference. So let's do a quiz. I'll leave this up for like 5 seconds if this is any faster to get to Mentimeter. And then I'll just switch over to Mentimeter. Is this any faster? Yeah, okay. If it's faster for some people, I'll try to put this QR code in each time. Okay, I'm gonna pop over to Mentimeter now. And here's the first question. Mentimeter will not let me make actual quiz show quizzes with picture responses, so we're gonna have to take the fun away of the leaderboard for this one, but I think that's probably okay. Here's the first situation. What would our human operator see if we were working with VSFS/ext2 and we had just updated the inode and nothing else? For clarity, this diagram that I was stepping through, I put on the course webpage alongside today's lecture if you want to have a copy of that up on your screen while you're taking a look at this. So I'm going to give you like 5 seconds to answer this question, and then we'll think about this together. Okay, I'm going to reveal what you have answered. Okay, all right. So this is just updating the inode, and keeping in mind that our inode contains information about our file, like the file size and the direct block pointers for our file. Okay, drum roll, and we're going to reveal that what I've marked as the correct answers here. The correct answers here are that we're going to see a corrupt image. If I open this file up in Microsoft Paint again, what I'm going to see is the block pointer that represents the data that was originally there, and then the new block pointer that has something. I didn't write the data out for this file. I didn't make that last change. I didn't write the actual data to the data region for this thing. And so one block pointer still points at the beginning of the picture that I had in the first place, and the other block pointer points at, I don't know, whatever happened to be there before. And so it's going to show up as a corrupted looking image. The other result is that we're going to see that the file size has changed. This is in our inode as the number of bytes that this thing has in it, and it will have been expanded to be whatever the new file size would be after we've added this new block to the thing. The disk space calculation here, when our operating system is calculating disk space for how much is free on this volume, it's not looking at the inodes. It's not going through every inode and adding up all the bytes or all of the direct block pointers that are here, but instead it's referring to the data bitmap. It's calculating how many blocks are free or not free purely using that data bitmap because it's able to calculate this really, really quickly using some specialized instructions. Are we all on the same page about this? It's okay? Okay, all right. Let's go to, is that a head scratch or a question? Okay. Let's move to the next one. Okay, so what would we see? Now we're thinking about exFAT specifically. What would we see if our machine crashed just after we had updated the FAT but nothing else? So we haven't updated any directory entries, we haven't updated the cluster heap, we haven't updated our allocation structure, just the FAT. I'll give you about 5 more seconds. Okay, I'm going to show what you have answered so far. Okay, so lots of people are thinking less available disk space, and lots of people are thinking no observable change. I'm going to reveal what my correct answer here is, and it's no observable change. Our operating system is using that allocation structure for representing how much space is available on this volume. On exFAT, we have an allocation structure. I'm going to come back here in just a second. We have an allocation structure here in the form of this allocation bitmap that's in a directory entry in our root directory that then refers to a cluster in the cluster heap that tells us which of these things or which of the clusters are used and which of the clusters are not used. The FAT and this cluster, this allocation bitmap cluster, are two fully separate things. They're two fully separate things, and our OS is just going to use this allocation bitmap for representing disk space. The other options here, a corrupted image, that's actually a reasonable choice to think about. That's a super reasonable choice to think about because when I go back and open this file again, if I'm looking at the FAT, I'm going to build a cluster chain that has 2 clusters in it now, where it used to just have 1. But the other thing that we've got is the file size. The file size is in the stream extension, and the stream extension is in the directory entries for this file. When I'm opening the file, my program like Microsoft Paint isn't going to know anything about clusters. It's going to be told there's this many bytes in the file, and I'm going to read that many bytes. It's never going to even try to read the new cluster because it doesn't know that the new cluster exists. So while we'll build a cluster chain that consists of 2 nodes now, we're never going to get to that second cluster because the directory entry was never updated with the new file size. Same thing with the bigger file size here. We're not going to change that directory entry, so we're not going to make any changes to the file size. Does that make sense to everybody? Now, I want to be really clear that if we were thinking about older versions of FAT, like FAT32, there is no allocation structure. And so if we were looking at FAT32, the FAT itself is what is used to calculate the available disk space. That part is then true. We look for these non-FFFFF entries in the FAT to decide whether or not a cluster is allocated or not. But because we're talking about exFAT here, there's no observable change. We're not going to see anything. All right, here's the next one. What would our human operator see if we crashed after just updating the data bitmap? So nothing else, just this data bitmap, just the allocation structure here. I'll give you about 5 more seconds. Okay, I'm going to reveal your responses. Okay, so there's very few no observable change. kind of a mix of bigger file size and corrupted image, and then lots of people saying less available disk space. So I'm going to reveal my response here. Yeah, 100% less available disk space. If we've just updated this allocation bitmap, all we've said is that this cluster is not free anymore, or this data block is not free anymore, and we can't use it for anything else. So we haven't made any changes to the actual file contents. We haven't changed the inode that has this file size. We haven't changed the inode that has the direct block pointers. We haven't changed directory entries that have the file size. We haven't changed the fat that has entry to the next cluster in the cluster chain. So the only thing that we'd ever be able to see about this is that there's less available disk space. All right, I'm going to move to the next question. What would we see if we crashed after updating just the data region and the cluster heap? So in terms of the picture that I'm showing you, all we've done is change that cluster or that block to have that picture of me in it, the new block, the new thing that we've added for this. I'll give you about 5 more seconds. Okay, I'm going to reveal your answers. Okay, so there's kind of a split. It looks like a split between all 3 of the options except for less available disk space. I'm going to say that a corrupted image is a reasonable choice. We've added something to this file, but we haven't made changes to the metadata about the file. We changed something about this file, so maybe a bigger file size is a reasonable choice. We've used a data region block or a cluster, so we could theoretically have less available disk space, but I'm going to say here that it's no observable changes. If we've just added that picture to the cluster heap, or we've just added that picture to the next block in my data region, we're not going to see a corrupted image here because our inode and our directory entry and our fat will never have been updated to say that they're using this new block or this new cluster. And so while that change has been made to the data region, that those bits have been written, that picture is there if we were to look at this block, any program that we're using to interact with this file system are not going to be able to see those changes. It's not even aware that that other block is being used by this picture right now. Similarly, a bigger file size, because we haven't actually changed the structure for this file, we haven't changed that stream extension, we haven't changed the inode, the size of the file is going to remain the same, even though the data was written to the cluster heap or the data region. Less available disk space. This one here, we haven't written to that allocation structure, and the allocation structure is going to be the one that says whether it's free or not. We've written data to the data region. We've written that to the block. We've written it to the cluster. But it's still able to be used by something else because we're going to look at that bitmap to see is this free or not, and it's still marked as free right now. So we'll be able to go and use that block later. So no observable change here is the correct answer. We're not actually going to see any change in the file. We're not going to see any changes in the free space in our file system. We're okay with that? We're good? Any questions? I need to stop and take a drink. This is a million times less fun without the leaderboard. I don't know what about the leaderboard makes this so much more fun, but maybe I should have had you all fill in slips of paper with your name, and then I don't know. Here's the next one. What would our human operator see if we crashed after updating the data bitmap and the inode or directory entry for this? So we made changes to the stream extension, and we made changes to the inode, and we updated the allocation structure in both of these things. So now we're making 2 changes to the file system instead of just 1. I'll give you about 5 more seconds to respond. Okay, I'm going to reveal your responses. Great, okay. So if we've updated the data bitmap and we've updated the files metadata, so in the inode or the directory entry, I think that we will probably see a corrupted image, yes. We've updated the direct block pointer, and also we've updated the file size. So for both the different kinds of file systems that we've got, we've indicated that there's more data here than there was before. A bigger file size? Yeah, 100%. We just updated the directory entry in the inode for this file, and that's where we're keeping the file size for these things. So our file size is going to look a little bit bigger. And the data bitmap will have also been updated to represent that we have used this cluster or this block. So we're going to see something here. And so we're going to see all 3 of these different changes. The outcome of this is actually slightly different. I'm going to let you ask your question first. Yeah, what's your question?
What happens if, like, when the directory entry is updated so that it says that it's a bigger file size, but that's not updated?
Okay. Good. We are 100% thinking about the same thing right now. There's going to be a big difference between the way that VSFS and ext work versus exFAT, because we're going to update the inode, and it's going to point at the direct block pointer. So we've made 2 changes with one go. But with exFAT, if we say that the stream extension says this file is bigger, where's the next cluster? Where is the next cluster? We didn't update the FAT. So if we go back and try to build a cluster chain for this, what we're going to find is that we're going to try to go to the next cluster, but it's FFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFF domain. So what does happen? What would be, now I want you to think about this in terms of you are writing the code to implement a read call. What would be the right response? I am asking you, but you could say I don't know.
But I'm thinking it would just be like
Okay. A read system call or a read function call, remember, tells us how many bytes were read. And so I think a reasonable response here would be the -1. There's an error. I think there's more bytes here, but I don't know where they are. I don't know where they are. So I'm just going to give up and not give you anything anymore. This is very much different data structures are inconsistent with each other. The directory entry says there's this many bytes, but the FAT says that there's only one cluster. The bytes is more than one cluster. These two things do not match. They don't match. This is a very clear inconsistency between these data structures. So good. Thank you for pointing that out. Thank you for pointing that out. Any other questions? All right, okay. What would we see after updating the inode or the directory entry, so the stream extension, and the data region or the cluster heap? So we haven't updated our allocation structure. We haven't updated the FAT. I'm going to give you about 5 more seconds. Okay, I'm going to reveal your responses now. Okay, so we're kind of split here. The biggest choices are a corrupted image and a bigger file size. Less available disk space and no observable change are kind of like, they're there, but they're not the top responses here. We have updated the inode, and we've updated the stream extension directory entry. The inode and stream extension directory entries have direct block pointers, and they also have the file size for this. We have made changes to the data region. So I've got my picture of a cat, and I've also written the picture of me beside it. So a corrupted image here is actually probably not what we're going to see. I'll come to you in just a second. We're probably not going to see a corrupted image because we've updated this directory entry that says we've got this many bytes in this thing, and at least with VSFS and ext2, we've got 2 direct block pointers, so we're going to be able to figure out where those things are. And we've written to that block that we just added to the direct block pointers. So our image is not really necessarily going to look corrupted. A bigger file size, yes. Less available disk space, no, because we didn't update our allocation structure here. We didn't make changes to the data bitmap itself to say that this block was used. So for me, the correct answer here is it's not a corrupted image. We wrote that block. We wrote the change to the file. We actually made the change to the cluster, and we actually made the change to the block. We updated our inode, so the file size does change, and the direct block pointers change. So the file size does increase, but our less available disk space does not change. We haven't updated that allocation structure. Yeah?
Would it result in a corrupted image with the exFAT because it's relying on the FAT to point to the next cluster?
That's a great question. And so I'm going to retcon this and say that we are using the no fat chain attribute. So we don't have to update the fat. I'm just going to correct my little mistake here that I've forgotten about. But if it was non-contiguous, yeah, it would be corrupted. It would look corrupted because we would be in the same situation we were in the last scenario where we don't know where the next cluster is for this thing. But let's say that they are contiguous. Let's say that they are contiguous. They're right next to each other, and we don't have to build a cluster chain for this thing. Yeah. Okay. So good question. Good point. Okay. Any other questions about this? All right. Okay. The same thing, except now it's a little while later. I've continued to do stuff on my operating system. I've continued to use my operating system. I'm opening up my diary and writing about how my cat bit me today. I'm making changes to the file system. I'm adding more stuff to the file system. I'm deleting files. I'm reading things. I'm doing all sorts of stuff with it. What's it going to look like after some time has passed? I'll give you 5 more seconds. All right, I'm going to reveal your responses now. So lots of people are sticking with bigger file size. I think that is a correct choice. Yeah, you should definitely stick with bigger file size because we made that change to that directory entry and the inode. We made that change, so the file size is going to stay bigger than as it was before. Less available disk space. We're still not making changes to the allocation structure here. So we're not going to have any reported difference about the amount of disk space that's currently available to us. No observable change is a reasonable choice. It's a reasonable choice, but I'm going to say some arbitrary amount of time has passed. Maybe it's hours, maybe it's days. The correct answer here is going to be eventually we're going to see a corrupted image. The reason we're going to see a corrupted image is that our allocation structure was not updated. As far as our operating system is concerned with this file system, that block that we wrote to the cluster heap, to the data region, or the cluster that we wrote to the cluster heap is not used. The stream extension kind of points at it. Our inode has a direct block pointer to it, but the allocation structure says that block's free. Nobody's using it. Write whatever you want there. And so what's going to start to eventually happen is that as I write my journal about my, I'm going to say diary explicitly because I do not want to overload this term. As I write into my diary about my cat biting me today, that Word document's going to show up in that cluster or block. And when Paint tries to open this, it's going to be the picture that I had of my cat originally, and then whatever it thinks this Word document is as a bitmap. Yeah.
Would this ever actually happen in practice? Because I would assume that the bitmap would be updated right away with this one.
So that's a great question. I'm going to go back to this diagram. Oh no, my screen is gone. Oh, it's because it's turned off here. This diagram that we've got for these is that our data bitmap here is in a block that's physically separated from the block that contains my inode table, and is definitely physically separated from the data region itself. Blocks, remember, are bigger than a sector size, and we don't know too much about disks yet, but our guarantee is that a sector is an atomic thing. So I'm guaranteed to be able to write 512 bytes to my disk at a time. The data bitmap and the inode table are much bigger than 512 bytes. So it's definitely reasonable that I could write to the inode table and not make changes to the data bitmap. It's definitely reasonable that I could make changes to the data region and not the data bitmap, because they're very far away from each other and they're much bigger than 512 bytes in size. The same is true here for exFAT. I could be making changes to the cluster heap, and I could be making changes to the directory entries here, but they're physically far away from each other, and cluster size is going to be much bigger than the sector size. So I'm going to be making small changes to this thing kind of over time, as opposed to all in one bulk atomic unit change.
So it's possible for you to write to one block and then another one to just write over it, technically?
Yes, exactly, yeah. All right, I'm going to go back here. I've got one last question for you. This question is different. This question is not about making changes to the actual data, but it's making changes to the name of the file. So what would happen if we crashed while I was renaming a file, so making the file name longer, not adding to my picture, but changing the name of the file and making it longer. And I've just updated the stream extension, but not the file name directory entry for this thing. Oh no, okay, I'll give you like 5 more seconds. We're over time, I'm really sorry. I'm gonna review responses. Good, good, I'm really delighted that you're all picking those ones. Yeah, 100%. If I don't update the file name, it's just gonna start reading whatever crap happens to be there. It's maybe the file for the next entry set. It's maybe the stream extension for something else. Maybe it's data for something. No, it's not gonna be anything but other directory entries. This is also conceivable to happen if we have a situation like we've got directory entries that are scattered across clusters and they're not contiguous. They're not physically next to each other. It's possible for this to happen because one write might change the next one. All right, so thank you all for participating in that. You should be able to choose an appropriate rate level given requirements. And at this point, you should be able to describe what a human operator might see in files when a file system is in an inconsistent state. I hope that you all have a good rest of your day. Thank you for 2 minutes of your extra time, and I'll see you all on Friday. Bye, everyone.